Nice. So yeah.
Is the exam delayed by any means?
No, the exam's still going to be tomorrow. The people who miss it, if there are enough of them that like I need to schedule an individual session, I'll figure that out. So yeah, I'm still planning the exam this year because I want to be able to let people select which exam they want to retake soon, and my life gets very unpleasant when I have like a pile of grading in addition to the normal week block as opposed to grading over the weekend. So I really want to get it graded on Saturday, which means it needs to happen on Friday. Cool, let's just go through the list and see how people feel. How do people feel about composing with a trig identity? Yeah, so
I understand most of it. The one that I don't really get is
So the upshot is that on these trig identity problems, you can theoretically avoid thinking about tangent completely. Okay. Because even if I ask you something about tangent, what is tangent?
It's sine over cosine.
Sine over cosine. So if I ask you to prove a trig identity, this isn't always the most efficient way, but that's okay. One of these has to do with tangent, I hope. Yeah, so let's suppose I ask you to prove that trig identity. One strategy is you just say, well, screw it. Let's write everything in terms of sine and cosine. And secant too. What is secant in terms of sine and cosine?
1 over cosine.
Yeah, cool. And people are planning on maybe putting those translations right on their note card. Yeah, if you have them in your head, then I guess you don't need to, but what's the right thing to put on one person's note card isn't the same for everyone. So secant squared becomes 1 over cosine squared x plus 2 sine x over cosine x. And now you're in a situation where things look more complicated at all. But it's now only a bunch of sines and cosines. And so to prove this, the only things you should need are being able to do algebra, right? Knowing that when you square a sum, you should FOIL it out. Knowing that you should get a common denominator to add fractions, knowing what cross multiply means, stuff like that. You should know stuff like that. And then also the Pythagorean identity. Sine squared plus cosine squared equals 1. Those tools will be enough to prove anything I ask. Should we keep going through this one?
I think you can figure it out.
Okay, yeah. Okay. See, there's like something being squared, so maybe you'll want to FOIL that eventually. I see a bunch of fractions, so common denominators and adding fractions will probably be handy. Cool. Otherwise, people feel pretty okay about proving trig identities. Yeah. The things to remember are how does algebra work? Right. Make sure you're careful with fractions. You add fractions by getting a common denominator. You can always just multiply fractions. Right? When you multiply a fraction by another fraction, you just multiply numerators, multiply denominators. If you have a fraction equals another fraction, you can cross multiply and make your life easier that way. And then remember the Pythagorean identity. Cool. Now let's just proceed down. How do people feel about the problems in the sample about inverse trigonometry and composing inverse trig with trig? Yeah.
I've been struggling to use the law of cosines to find an angle.
Okay. Yeah. That'll scroll us farther down. It'll be in the law of cosine stuff. Alright, so let's see. I think this problem will be one where you'll use law of cosines to find those missing angles. Sorry, you can't use the law of sines because you don't have opposite information. So let's do some setup. Let's write down how to use the law of cosines to find these. So what does the law, which one, I'm going to do one of the three, not all of them. Which one should I do, A, B, or C?
Which one are we doing?
Bottom right.
Okay. Let's just do it.
Let the alphabet make the decision.
Yeah.
So, not going to walk on the board because it needs to be recorded. So, in this I've stopped there. Alright, so I just want to find that, nope, not that angle, this one.
We also have a 9.
Oh, my bad. No, that's my bad. I'm holding it on the screen. So, let's start by just writing down what the law of cosine says here. So, start there. What's the statement of the law of cosines as applies to this particular triangle?
It would be 8 equals
Squared.
Oh, 8 equals squared. 9 squared plus 7 squared minus 2 9 times 7 times cosine of A.
Yeah, cool. So, the law of cosines looks like the Pythagorean theorem, but it's not a right triangle, so the Pythagorean theorem can't apply here. There's some error term and it's captured by cosine. I don't know, what do people think? Are they just going to have the law of cosines on their note card someplace predictable? A thing to note is, because this is an easy thing to screw up when you use the law of cosines. Those two things have to be opposite each other in the triangle. If they're not, then you're finding some other angle instead. Another thing worth noting is because of how order of operations works, you should think of all of that as being lumped together, separated from the 9 squared plus 7 squared. Because just an error I see an awful lot is people will do the 9 squared is 81, and they'll add 49. And then they'll subtract that from 2 times 9 times 7, and then multiply with the result by cosine. Which, right, just isn't the way order of operations works. So let's carry on from here. We want to know what A is, so let's start by getting cosine A on its own. So, what should we do?
Take that whole thing in parentheses and move it to the other side of the equal sign.
Sure. If we're going to do that, then I'll also move the 8 to the other side of the equal sign. So I'll do that by adding this stuff and subtracting 8 squared from both sides. So 2 times 9, well, let's do some multiplication here. 18 times 7, because that's 2 times 9, times the cosine of A equals, this stayed put, 81 plus 49 minus 64. I buy that as reasonable enough. And you know what, as long as we're doing it 18 times 7, I know you have calculators for stuff like this, but I get 126. Does that agree with someone who did the computation independently? Okay, cool. Then I'm happy. So that 18 times 7 is actually 126. All right, what should I do next?
Add 8149 and then subtract 64.
Cool. Yeah, let's evaluate this side. So 81 plus 49. Gosh, 1 plus 9 is 10, so you carry the 1. 8, 9, 13. So 130 minus 64. I get 66. Cool. That agree? All right. So, what next?
Divide by 126.
Divide by 126. So cosine of A is 66 over 126.
The inverse cosine of both sides.
Cool. I don't know, if you wanted a numeric answer, 66 over 126. Well, it's a fraction that should be simplified, but it's definitely not something you see on the units level anyway. Because, right, it's even divided by even at least. But, what is that?
Punching that into my calculator, I get 58.41
Cool. Degrees or radians?
degrees.
Nice. And I think the way I wrote the solution, I plotted the answer in degrees and in radians, maybe. The problem solving doesn't specify which one it wants. And if I ask you this question, it's like an open-ended. If you give me degrees or radians, I'll be happy. If it were a multiple choice and I provided a bunch of options, you would look and see if the answer seemed to be in degrees or radians, and then make sure that you aren't blank. Nice. I feel pretty good. Cool. So notice the only step we needed a calculator for on this was evaluating that inverse cosine. And I do try to design my exams to be as non-calculator needed as possible. So I might even, if I were writing a question, this is a multiple choice, I might even give the option of inverse cosine of whatever 66 over 126 is simplified, and then say what that is approximately. Was that helpful in just the process of how to think?
Yes.
Okay, excellent. Yeah, so the mistake that I see an awful lot of people make, especially on the exam, because it's like a high stress situation, so it's easy to make like really silly mistakes, is acting as if there are parentheses around all of these. There aren't. Nice. Hopefully that was helpful to people. And everyone's being very quiet. So, feel free to get out. What happened to the negative sign in front of this too? Well, our first move was to add this to the other side, which was not the first move I was expecting.
What would you have expected?
Something absolutely equivalent to it, but I would have had a negative sign that I would have had to divide by. The thing I would have wanted to do is subtract 9 squared and 7 squared to the other side, and then divide by the negative. It's not your strategy is the same amount of work and is arguably better because it gets rid of the negative sign. It's just not what I was expecting. And in fact, yours is safer because if you leave the negative sign, then it's easy to accidentally lose the negative sign. How many people are just thinking that it might be worthwhile putting on the note card the thing you get when you take the law of cosines and solve for cosine of A? Yeah. All right, you can do that algebra in advance. And just say, well, the law of cosine says this, but it also just says cosine of A equals some stuff divided by some stuff. Sorry, off the screen. God, you can clue you in with some algebra that you think might be likely to show up on the exam. How many people are already thinking that they do that? Yeah. Now, feel free to. Cool. Oh, no, I don't want that. So, barring any specific questions, inverse trig stuff. How do people feel about reading off an angle from a right triangle using inverse trig? That first set of problems go okay? All look reasonable? Cool. How do people feel about, oh, that which shouldn't be capitalized. Just reading off what quadrant a thing lives in by the fact that it's inverse trig or something. Does that seem okay? How many people, when they approached this, just took the strategy of let a calculator tell you what this inverse trig value is, and then just answer what multiples of 2 pi of it's between? Yeah, that's not a terrible idea. It's maybe harder than is needed, but I think it'll be good enough. Yeah.
We do one with like tan or
Sure. How about this last one?
sure.
So, the false thing to note is that -6 is supposed to make you think that's a really big number, so maybe this just doesn't exist. But does it exist? Yeah. Inverse tangent's domain is everything. Inverse tangent always exists. If you now want to figure out what quadrant it's in, a thing to remember is that range of angles is the range of arc tangent. Okay, zoom out. Ooh, I can physically zoom out. There we go. So what quadrants can you eliminate just by the fact that it's arc tangent?
2 and 3.
2 and 3. Alright, so arctan is -6, so I want an angle whose tangent is -6. If this angle were in quadrant 1, what could you tell me about tangent? Positive or negative? Positive. So the two ways to think, alright, our tangent is sine over cosine. So that would be positive over positive, positive. Or tangent is a slope. Tangent is the slope of the line that goes up at that angle. That blue line I just drew, positive slope or negative? Positive. So, not this one. There's a line that has -6-ish slope. And what quadrant is that in? 4. So, a way to think about a bunch of things is, there's another inverse tangent. Inverse tangents either in quadrant 1 or quadrant 4, so it can't be quadrant 2 or 3.
How would you figure it out if you use like sine over cosine?
Sine over cosine? Oh, sure. So the step where you think about sine over cosine is you need tangent to be -6. That means you need sine over cosine to be negative. In quadrant 1, is sine positive or negative? Is cosine positive or negative?
Positive.
Is positive divided by positive positive or negative?
Positive.
Oh, but I need it to be negative. So, it's the same process. You're just using the plus or minus to eliminate options. Yeah.
For the range of sine, it's going to be the same as tangent, right?
Yep.
And then for cosine, it's 0 to pi. Right?
Yep. So which quadrants is that?
that 1, 2.
Yep.
So I don't know if this is like a little trick way of thinking about it. You say that tangent's odd, so you can bring up that negative.
Multiple negative.
Does that always mean that, like, since it's between 1 and 4, if you bring out that negative, does that mean that it's going to be a 4?
With one other fact. When you take the inverse trig of something positive, it's definitely a quadrant 1. If you stick a negative in front of it in quadrant 1, you're a quadrant 1. So yeah, you can do it that way. As long as you also remember what you do for positives. Yeah.
So can it never be quadrant 3 then?
Yep, none of the inverse trig functions hit quadrant 3. And one of the reasons for that is picture an angle in quadrant 3. You could make that angle simpler while keeping the same sine value by putting it into quadrant 4. You could get a simpler angle with the same cosine value by putting it into quadrant 2. You get something with a simpler tangent value by putting it into quadrant 1. So quadrant 3 is more complicated. Any angle in quadrant 3 is more complicated than it needs to be for any one trig value.
Is it just not possible or not possible with our current knowledge?
Oh no, none of them have quadrant 3 in their range.
Well,
Because any angle in quadrant 3, so inverse trig functions only care about one trig function. They only care about tangent if it's inverse tangent. If you have an angle in quadrant 4 and you want tangent, well, the slope of that line is the same as the slope of this line. And this one just looks like a simpler angle. It's in quadrant 1, it's acute. It's not down here either negative or bigger than that.
okay, it's just reminded me of something. We were doing something with obtuse angles and acute angles. How do you know which one you need to calculate for?
Oh, cool. So this is like the inverse sine problems where there are two options?
Yes.
Yeah, nice. So let's, in fact, let's go and I think there's a problem on here that specifically has that as the prompt. So here is the decision-making scheme to use. So let's look at this false triangle. 5, 1, 15 degrees C. So the first thing to ask yourself is there even one option? And to do that, write down what the law of sine says. Solve for the sine of C, see if it's a valid output. So, doing that, sine of C divided by 1 equals 5. Nope, sine of 15 degrees divided by 5, and either with the calculator or without. Tell me, is that thing that I just pointed an arrow at bigger than 1 or less than 1? Less than 1. And in fact, you could have figured that out without a calculator. Sine of 15 degrees is already pretty small, and then you divide it by 5. It's not going to get bigger. So you didn't need a calculator to do that, but you have a calculator, so why not use it? That's less than 1. That's a valid output for sine. So because of that, you're in a situation of 1 or 2 solutions. And now let's decide which. So to decide which, you need to ask yourself, is it possible that C is obtuse? And to answer that question, you ask yourself, is the side opposite C longer than the other given side? And you're obviously not going to write out that full sentence on the exam. But now answer that question. Take the side length opposite C. Is it longer than the other side you're given in this problem? No. 1 is less than 5. So that means C cannot be obtuse. So the only option for C is the acute option. Is that kind of the decision making you wanted to see? Or do you now want to see, like, how do you find it?
How to find it as well.
Oh, cool, let's find it. So
Both is useful though.
let's find it. So right now I have sine of C equal to sine of 15 degrees over 5. And how many people in, like, their own walk would tend to want to replace that sine of 15 degrees divided by 5 with, like, a decimal approximation? Cool, then I want to know what C is. Inverse sine will give me the acute option, because the only angles inverse sine is allowed to give are either acute positive angles or acute negative angles. And negative angles can't appear in a triangle, so I can only get the acute positive angles. So inverse sine will give me that. C equals inverse sine or arc sine of the sine of 15 degrees divided by 5. And I don't think there's any real way you can simplify that much. I guess using half angle identity, you could know what the sine of 15 degrees is. Yeah.
I thought normally in doing a lot of science you cross multiply, don't you?
Ooh. That's why I didn't. Division by 1, I could just ignore.
Oh, yeah, yeah.
Usually you take this 1 and you multiply it
Move
over
it
to the other
there.
side, but
Okay, but
because
it doesn't
it's
matter
one,
which
you-
one, that doesn't mean anything.
so that's how you would find the acute option. If this angle could be obtuse, how do you find the obtuse option? So this doesn't have an obtuse option, so you wouldn't do this on this problem. But if you wanted the obtuse option, because this thing can't be obtuse, what I'm about to do is like long in this context. You would do C equals 180 degrees minus sine inverse of sine of 15 degrees divided by 5. And then get a decimal approximation by using the machine. Make sure you're in degree mode because things seem to be in degrees. Let's do like the one solution or two solution decision making for one other of these triangles just to see it in action. Oh, sure, we can just jump straight to 47. Let's compute the area of that triangle. Give an exact answer. Yep. Still want to do it?
Yeah, sure.
All right. What's the formula for area that we got?
1.5 times.
Times 4 times 5 times the sine of 45. Yeah.
Nice. And maybe I'll put the picture on just so I have it. That doesn't look like a very good 45-degree angle, but whatever. Oh yeah, so none of the pictures that I'll provide on the test, you should trust that they are correct to any form of scale.
And these side lines have to be like adjacent to the equal, right?
Yep.
Okay.
Yeah, so if you're given a problem where you have like that situation and you need to find the area, you don't have a formula that just does it.
Yep, on the other side.
You'd have to find more information first. You could stop as soon as you have enough. The other side length would certainly be good enough. And I think that is the first thing you find that would be enough. And then, right, it says I want an exact value here and not a decimal approximation. So I guess you also have to know what the sine of 45 degrees is, but you know the sine of 45 degrees, it's on your given as well. So plug that in and simplify.
Could we do a log sines with an obtuse angle?
Sure. Sure. In fact, let's actually go back to 36. The rest of the way out so that we see all the subtleties.
Okay.
So far we talked about 1. B will be something interesting that happens. Let's see what happens for B. C5, 1, 15 degrees. And again, I haven't tried to draw it to any sort of correct scale. The side length 5 should be 5 times as long as the side length 1. So let's write down the law of sines and see what it tells us. So it looks like I get the sine of C should be divided by 1. Nope, divided by 5 should be the same as the sine of 15 degrees divided by 1. Oh yeah, so that's something to look out for. When you use the law of sines, make sure you're dividing the correct things by the correct things. They come in pairs that are opposite on the triangle. All right, so let's start by just getting sine of C on its own. So what should I do? Cross multiply, and I'll even forget about that divide by 1 because it doesn't matter.
Sine C equals 5 sine of 15.
Cool. And if you want to know if there are any solutions, you need to somehow decide whether or not that's bigger than 1 or less than 1. And like maybe you could do it by like using some half angle identity stuff to figure out the sine of 15 degrees, but that seems harder than just using a machine. Using a machine, tell me what you can about 5 times the sine of 15 degrees.
Close to 1.2.
Close to 1.29. I'm going to round that further, 1.3. So what can you say? What can you tell me now? Bigger than 1. So what's the conclusion? Can sine? So this says that C is an angle whose sine is bigger than 1. Does such an angle exist? No. No solutions. As soon as you get sine of C bigger than 1, then there are no solutions.
Or like, will we have a problem on exam just like 36, or will we have to actually provide said answer?
I would regard something of the form of 36 to be fair game, where like I give you the setup and you just need to tell me how many solutions exist. Because I think that tests interesting information. Do you have this ability to classify how many solutions without requiring you to get bogged down in doing the algebra? Well, yeah, so I guess like here's another thing. If I give you this as a multiple choice problem, I don't like to have only 3 options. So I'll probably say there are 0 solutions, 1, 2, 3, or 4 solutions or something. But there can't be 3 or 4. It's just, they're just not that's not a possibility. So there's the no solutions and you just stop. So I guess this last one better have 2 solutions. So let's see. C2, 15 degrees, 4. So you play the exact same game. Sine of C divided by 4 is sine of 15 degrees divided by 2. Gosh, sine of C is 4 over 2 times the sine of 15. And that's 2 times the sine of 15 degrees. And same question, so let's just answer the 0 solution, 1 solution, no solution. How many solutions do I expect this? Well, is that thing bigger than 1 or less than 1? Less than 1. By busting out a calculator, I guess. I guess alternately, if you already told me that when you multiply it by 5, it's about 1.3, multiplying by 2 will be less than half of that. So, at least 1. So I guess if you're crunched for time, there's a check that didn't take much time. If you get to the end and you decide to put off a problem like this till the end, if you get down to here, you're at a 50-50 at least, and now your week's a falling walk, so you'll probably get some good credit if you just say there's at least one solution and stop there. Let's keep going. Let's determine whether or not there are 2 solutions. And I don't know, let's see, just by looking at this problem, only 1 solution or 2 solutions? 2. Why?
Because 4 is greater than the other side length that we have.
Nice.
So it could be the biggest side length.
4 is bigger than 2. I don't know this missing side length yet. So I can't check whether it could be the longest, because the only way I could find it would be by already knowing what the missing angle is. So, obtuse is possible. And now, let's see what we have. Let's list the acute option and the obtuse option and see what happens. So, right here, I know that the sine of C is equal to 2 times the sine of 15 degrees. So, well gosh, how do you find that angle then? If you know it has to be acute.
Plug it into your calculator or anything like that.
Oh, sure, like maybe you can take this and get a decimal approximation.
Yeah.
And then you would plug that decimal approximation into inverse sine. Yeah, that's not bad. I'll write down the exact value instead. C equals sine inverse of 2 times sine of 15 degrees. But you know what? With a bunch of these, the exact values get complicated too quickly, so let's just get that decimal approximation. What is the acute solution you get?
31.17 degrees.
Nice. How do you find the obtuse solution?
Well, maybe minus the exact.
Mhm.
Or the decimal approximation.
I really feel like acute should have 2 C's in it. So, what is that approximately?
148.83.
Cool. So in each case we now have C. I guess if this problem didn't even ask us to do that, right? It would have a stop as soon as we knew there were 2 solutions. Should we finish out finding the other entries in this triangle? Sure. So I guess there's still a missing angle and a missing side. What should we do first?
Well, actually, no, we have
Missing angle.
Yeah, we have 2 angles.
Missing angles. Well, there's only one missing angle in a triangle. Angles add up to 180 degrees. Find the missing angle. So, other missing angle, I guess it'll be 180 degrees minus 15 degrees minus, well gosh, let's use a decimal approximation, 31.17 degrees. That is whatever it is.
133.83.
Cool. I might not necessarily believe that last digit of the decimal expansion because I rounded off stuff beforehand, so it might be wrong, but that's okay. Probably I usually grade based on are you accurate at least to the 10th of a degree because that's small enough. Yeah.
Do we need to find the acute option side? Well, I mean,
Yeah, let's find the other one. And notice, this angle is obtuse. So when I say the acute option, I mean the acute option for the angle C.
Okay.
So when this sucker is acute, that one
This
is
the
obtuse.
angle.
So how do you find the, so let's do it in the obtuse case too. You would do 180 degrees minus 15 degrees minus 148.83 degrees.
You get 16.70.
16.70? Is that what you said?
No, 17.
17.
Yes.
Okay. Oh, cool. So here's something that's less surprising. If C is obtuse, then the other angles have to be acute. There's only one obtuse angle in a triangle. All right. Now, how would you find the unknown side length?
The sine of 133.83 divided by x equals sine of 15 divided by 2.
Yeah, cool. That looks like you could solve that for the missing side. I might even suggest this. I proposed two different versions of the law of sines when we first covered it in class. When you want to find the missing side, use the one that has the missing sides on top. It's equivalent, but it'll save you the cross multiply step. Nice. That look easy enough to solve? Cool. So was that helpful, I hope? Just that quick review of how to think through the law of sines problem? All right. So we have some law of sines, law of cosines stuff. We have some solve trig equation stuff. I guess we haven't talked about solve a trig equation. Yeah. 31, perfect. Yeah. Let's solve this trig equation in particular. Good choice. Because this one I think has all of the tools. 3 times sine squared x plus 4 cosine x plus 3 equals 0. Make that multiply more convincing. All right. So let's go through and try to solve this. So here's one option you do have. It might not necessarily be a valid option depending on what I want. You could graph this and get decimal approximations. That would even tell you like how many solutions to expect. Probably the answer is infinite, but the graph would also tell you if there are none. Yeah.
If you were to use the fact that cosine squared plus sine squared equals 1, would the 3 for the 3 sine squared, would that follow through?
Yeah, so you can replace the sine squared by 1 minus cosine squared, right?
So it'd be 1 minus 3 cosine squared?
Nope. So it'll be 3 times, and then I need all of sine of x to be multiplied by 3.
Oh, okay.
Yeah. Don't I make any silly mistakes like copying the top down on?
No.
Oh, okay. That just sounded like the kind of that people say when they're about to break bad news to you.
No, I just
Cool. So, does that look better than it was before? And now there's only one trig function involved. Cosine is the only trig function I see. So what step should I do next? Or like, what's the philosophy to use?
Combine or factor the 3 and
Yeah. In fact, opposite of factor, distribute.
yeah, distribute.
Yeah, I'm going to do another thing at the same step. I'm going to make a substitution to make it so I'm not worrying about trigonometry while I'm doing the algebra. I'll replace the cosine with a c. So 3 minus 3c squared plus 4c plus 3 equals 0. That looks like something you can solve? Yeah, I guess like quadratic equations, the strategy may be to factorize, but especially on things like the sample. I'm not careful to make sure that like algebra works out nicely. So 0% chance that it backdoors. Not to say it's impossible, just not probable. So, gosh, I like my squared coefficients to be positive, so I'm going to move everything to the other side. This isn't necessary, but so 0 equals plus 3c squared minus 4c minus 3 minus 3, so minus 6. That go okay? All right, quadratic formula. C equals negative b, so positive 4, plus or minus the square root of b squared, 16, minus 4 times a times c, all over 2 times a. And like, this number is what it is. I guess it would be nice to get an exact value if possible. Gesundheit. All right, so this is 4 plus or minus square root of 16 times 4 times 3 is 12. 12 times 6 is 6 times 72, right?
Yeah.
Yeah, that's... Oh, and I lost a negative sign. This 6 should have a negative in front of it. So 16 plus 72, all over 6. 4 plus or minus the square root of 6 plus 2 is 8. 1 plus 7 is 8. 4 plus 88 over 6. There's some perfect squares inside of that square root. I think I don't want to spend time pulling them out, but maybe it would be worth doing. So let's put that back. So that means that I have either cosine of x equals 4 plus the square root of 88 over 6, or cosine, I'm going to give myself some space, or cosine of x equals 4 minus the square root of 88 over 6. And I'm giving myself that space because at a glance, maybe those things are bigger than 1. Let's get a decimal approximation for each of them to decide whether the result should be there are solutions or there are no solutions. Cool. That agree with what you got?
Yep.
Cool. And minus. Is that acceptable?
The minus is, yeah.
Awesome. So, 2, which is bigger than 1. So this sucker gives no solutions. This is about negative 0.89-ish, 896-ish. Make sure my rounding is correct by just adding another digit. All right. So, this has no solutions. This has some solutions, though. How do you find all of the solutions for cosine? How do you find a false solution?
Find which one's less than 1.
Oh, yeah, but that's the one that's less than 1.
Yeah, and then you add 2 pi.
Yeah. So x equal to, well, do I want only the solutions in some, I want all the solutions on this problem, I think.
Oh, then you do pi, no.
No, for cosine it's plus 2 pi k. So the false solution is cosine inverse of that stuff plus 2 pi k. How do you find the second solution?
You do the pi minus that.
That's for sine.
It's for sine. Then it's pi, no.
Minus cosine.
Yep. Yeah, so maybe I'll close with not much time. Let's say this explicitly. That's how you find the second solution for cosine. You just stick a negative sign in front of the false solution.
Does it change when you find your third?
The rest of the solutions are taken care of by the plus 2 pi k.
Yep.
There are 2 infinite families of solutions.
Yep.
So you find one solution, it gives you an infinite family. Find a second solution that doesn't sit in that first infinite family. Now you have all of them.
Yeah, that does make sense.
So for sine,
Couldn't you do 2 pi and then minus the cosine?
yep,
Okay.
that's also correct. So put the 2 pi there or don't, both are fine. For sine, you get the second solution by x2 equals pi minus the forced solution. And maybe it's worth pointing out, the forced solution, second solution stuff behaves differently if you're saying cosine is equal to 1. If you get cosine equals 1, there's only one infinite family of solutions because basically the forced family of solutions and the second family of solutions are the same. Yeah. For tangent, there is only one infinite family. For tangent, you just do tangent inverse of whatever plus pi k. So tangent is the easier one to work with. And there's no weird subtlety for tangent. You'll never have a there are no solutions situation. For tangent. Tangent hits every output value. And it even hits them all in like a really consistent way. It's just forced solution plus pi k. There are 2 infinite families.
And then for sine, it's different.
Yep, for sine, it's find your forced solution using inverse sine.
Yeah.
Then you find the second solution by doing pi minus. And then you add 2 pi k's.
Pi minus, and the next one it's pi minus plus 2 pi k?
You always do the plus 2 pi k. So you get the forced solution.
Okay.
But now you only have 2 of infinite solutions.
Okay, that makes sense.
So now you put a plus 2 pi k in front of both of them.
Everything, yeah. Awesome.
Yeah.
Thank you.
Perfect. See you tomorrow.
See you later today.
Oh, yeah, that's right. You know what? I don't want to upload a 2-hour video, so we're going to stop now.